Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on February 26th, 2026, just yesterday. It introduces a scalable 3D reconstruction model that processes a 1,000 image collection in just 54 seconds, achieving an 11 times speed up over previous baselines. The paper is titled VGG-T3 Offline Feed-Forward 3D Reconstruction at Scale. And, as we'll see later, the shift from quadratic to linear scaling fundamentally changes what is possible for large-scale scene modeling. So Figure 1 immediately visualizes this scalability breakthrough. On the left, Panel A displays detailed 3D point clouds of major Rome landmarks like the Trevi Fountain, reconstructed from hundreds of unposed tourist photos in under a minute. Then, looking at the graph in Panel B, we see exactly how the method achieves this. The red and orange lines represent previous methods like VGG-T, which shoot up quadratically in processing time as the number of views increases. In contrast, the blue line at the bottom shows the new VGG-T3 model maintaining a flat, linear trajectory, allowing it to process 1,000 views in just over 50 seconds. Well, Figure 2 breaks down the architectural shift that enables this linear scaling. On the left, Panel A shows the original VGG-T baseline, which relies on global softmax attention, where every token attends to every other token, creating a quadratic bottleneck. Panel B presents the solution, a test-time training layer that replaces this heavy block. Instead of a massive matrix, the model updates a small internal MLP, marked by the fire icon, to compress the scene's geometry into its weights. The apply stage then uses this frozen MLP to process queries linearly, efficiently bypassing the memory limits of the baseline. Alright, having seen the architectural changes in Figure 2, Table 1 now quantifies the performance impact. It lists point map estimation results, splitting methods into quadratic baselines at the top and linear ones at the bottom. Crucially, VGG-T3 outperforms the competing linear baseline, TTT3R, across almost every metric. For instance, on the ETH3D benchmark, it cuts the chamfer distance error nearly in half compared to TTT3R, showing that efficiency doesn't necessitate a drop in accuracy. So, while the previous table listed accuracy, the visuals here in the top row prove the quality. Notice how the middle reconstruction from TTT3R is blurry, whereas VGG-T3 on the right matches the sharp detail of the slow baseline on the left, but finishes in just 58 seconds. Table 4 below confirms this efficiency. While the baseline crashes with out-of-memory errors on a single GPU, VGG-T3 handles 2,000 images easily, dropping to 48 seconds when distributed across 4 GPUs. Okay, having established the speed and quality, Table 6 investigates the specific design choices through an ablation study. The first row, softmax attention, represents the expensive quadratic upper bound the authors want to match. Looking at Item 1, labeled Scratch, we see that simply training a linear model from zero fails, yielding poor accuracy. However, skipping to the bottom row, the full method with shortconv 2D succeeds. It drops the error to 0.066, nearly closing the gap to the heavy baseline. So, Figure 4 summarizes the critical trade-off between speed and accuracy on the 7 scenes dataset. The vertical axis shows runtime in seconds, while the horizontal axis tracks the chamfer distance error, meaning points closer to the bottom left corner are ideal. You can see the original VGG-T represented by the red and orange dots high on the left. It is accurate but prohibitively slow for large inputs. In contrast, the light blue dots for TTT3R are fast but suffer from high error. Finally, the dark blue dots show that VGG-T3 successfully occupies the sweet spot, maintaining high accuracy while keeping runtime under 1 minute. Wrapping up, 2 takeaways stand out. First, VGG-T3 proves that compressing scene geometry into a fixed-size MLP is far more efficient than storing endless tokens. Second, this linear scaling enables the reconstruction of massive landmarks in seconds rather than hours, unlocking real-world scale for 3D vision. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.